Okay, so there are good examples in the notes. I'm going to try to create a couple more examples here just to give you something different. Hopefully I won't inadvertently do some of your homework. I haven't looked at it, so, I mean, I looked at it, but I don't memorize it, so anything could happen. Let's let t of f of x equals to, let's say 2 times f of x plus 3 times f prime of x. All right, now it's not hard to see that this is a linear transformation that goes from polynomial to polynomial. I'm going to think of it as being, to keep things simple, I'm going to think of it as being a linear transformation from P2 to P2. That should always be given in the problems I talk to you guys about, okay? So, you know, that's an ambiguity. I don't make you fight too much. So, polynomial, so P2 would be equal to the span of, let's say, 1x, well, let's say x squared, I'll do it the other way, x squared, x1. Be careful about that. There's two, either people do 1x, x squared, or, you know, the other way around. I'm going to go x squared, x1 this time. So I'm gonna let this be the basis beta, and I'm actually gonna you know, it's gonna be the basis for the range and the so here I'm gonna actually look at basically here, this in this case t is a mapping from v to v, and so I've got the same basis here and here, so we're not going to see much about the contrast of domain versus codomain, but that's okay. This is a nice simple example to get started with. Okay, so that's my choice of basis. So first thing you want to do basically here is get a handle on what does t do to a generic element of the space. So what's a generic polynomial of order 2? It's ax squared plus bx plus c, right? So, oh, by the way, first of all, is this a linear transformation? I hope so. I'm pretty sure it is. If it's not, we're going to get into trouble here somewhere. We'll see it. So, on the other hand, if what I'm doing works, we're going to write the linear we're going to write this formula, write this function in terms of linear transformations composed with a matrix multiplication. So, if we do that, that proves it's linear anyway. So, let's just forge ahead into the wild unknown and see what happens. So this gives us 2 times ax squared plus bx plus c, great, and then plus 3 times the derivative. Well, the derivative is 2ax plus b. Great, so if I clean that up a little bit, what do we got? I've got 2ax squared plus 2b plus 6a times x plus what? 2c plus 3b times 1. All right. And then I usually think about a picture, guys. I know, it's helpful to me. It's soothing. It's, I don't know what it is, but it is what it is. So if I have, you know, v equal to ax squared plus bx plus c, if I start with that, that's my point. And then I look over here, take my linear transformation t, what pops out? You know, t of v, which is equal to this stuff. I don't want to write it again. Right? Then on the other hand, I can trade, my vector space is 3-dimensional, right? So I'm really looking at R3 down here. So first of all, it's easy enough to find out what's the coordinate vector under the phi beta coordinate mapping of ax squared plus bx plus c. Well, it's just a, b, c. On the other hand, what's the coordinate, and we're also using the same basis over here, so phi beta of this guy, well, it's
2a.
Right, it's, yeah, I think I forced myself to write horizontally. Let's see here, 2a.
2b plus 6a.
2b, yeah, 2b plus 6a.
2c plus 3b.
2c plus 3b, very good. This is, you know, to be more symbolic, what we're looking at here, of course, is the coordinate vector of v under the beta basis. So, you know, this is the beta coordinate vector of the image of v. Now, then you just have to fill in the blanks, all right? So we're going from 3-dimensional to 3-dimensional. That means I expect a 3x3 matrix to get me from one place to the other. So what I do is I just kind of fill in the blanks here, okay? So I do
something times ABC is
some,
equals
yeah, exactly. Something times ABC it has to be equal to this thing up here, right? So I'm going to rewrite it 2A, 6A plus 2B. I have my reasons. 3B plus 2C. I'm writing it in order so the matrix multiplication is easier to see.
Mm-hmm.
So I'm happy we're videotaping this because you can see, okay, that's before, and then I just write the answer into the box.
So it's 2, 0, 0.
Right, 2, 0, 0. Oops, I'm using green, so sorry.
Let me check. Wait, it's fine. Green's fine.
That one's probably fine in here. 6,
6,
2, 0,
0, 3 is 2.
0, 3, 2.
So
And there you go. We
that
have now
is
successfully calculated the matrix of T with respect to the beta basis.
Ooh, that's cool.
And that's how you do it.
That's cool.
Again, to emphasize the procedure.
You
What?
might want to put what is use right, like the markers right down. Put the what is that correspond to in the put another line on that.
Another line on what? Oh, this. Oh, these guys.
Mm-hmm.
Oh, I see what you're saying. This is V beta. Thank you, Bailey. And this is T of V gamma. So one of my strategies for calculating these for explicit examples is simply to calculate what is the coordinate vector of V, like an arbitrary V.
Mm-hmm.
And I always make that simple. Like, don't make this complicated if you can't. I mean, you make it simple so you can see what you're doing. You choose the element in the natural way, like which respects the basis which is given, okay?
Mm-hmm.
And then you calculate whatever linear transformation you have, you calculate the image over there, right? Then you have to find the coordinate vector of that with respect to the basis of the codomain. That gives you the TV of gamma. And then it's just a matter of writing this and just thinking about what do I need here in order to get that, which is essentially the same calculation we did earlier for the standard basis. Now, of course, you can use I had a formula which is boxed, and you can work through that without drawing any of these pictures. And that's equally correct. I personally find it easier to think about with the picture. And students tell me the same, so who am I to argue? Okay, let's do another. This time I'll try to do something a little bit weirder, where we have actually a different domain in the range, in the domain, in the codomain and thing. So here, let's just take objects of entirely different type. Here's a good example. How about T of f of x is equal to f of x, f of x, f prime of x, f prime of x. Okay, and this is going to be, so we're looking at T is a mapping from, let's again say, P2 to, let's say, R2 by 2. And I'll use you might call them standard bases, I mean the usual bases. So here we'll let the basis beta equal to, I'm going to do it the other way this time, 1x x squared. And this one I'm going to let gamma have basis, the usual thing, E11, first row, and then second row, E21, E22. Okay. So my first order of business is to calculate what is this thing actually. So T of A plus BX plus CX squared. You notice that, yeah, be careful about this. This is the natural way to write it because I chose A to be the 1 and B and then C. I put them in order just to keep my life from being too miserable. And then, so that gives me A plus BX plus CX squared. A plus BX plus CX squared.
Which is
B
plus
plus
2cx
right.
equals 2cx.
Great. So I draw my little picture. Obviously, once you really understand, you don't need to draw the picture anymore, but probably not bad to draw it. I'm supposing this thing is V again, as usual. And here's your T of V, right? So first of all, I get coordinate vector ABC under the, oh no. Uno momento, por favor. Oh, no, 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 no. Oh, no, 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 no.
What?
In order for this to be reasonable, I mean, it's reasonable in some sense, but let's fix this example. I need to make these numbers. I want these to be numbers. How can I do that? Well, I can make this example reasonable. Trade my x, let's say for, we could trade it for 1, we could trade it for 0. I'm going to trade it for 1 because that makes for an easier adjustment what I've already written. But you could put a 2 there or a 0 there. 0 is less exciting because it makes certain things go away. I'm going to stick with 1. So that just means that x is equal to 1. Right?
Mm-hmm.
So that's easy enough to fix. There we go. All right. Now we got something. So this means, you know, that's t of, this is t of e right here, right? So under the gamma coordinate map, what do you got down here? The first thing, the 1, 1 spot, is a plus b plus c.
Mm-hmm.
The second thing is b plus 2c. Third thing,
B plus 2C.
b plus 2c. And then a plus b plus c yet again.
Okay.
So I need to be able to get
Something multiply ABC.
from here to here
Yeah.
by multiplying the matrix T, beta gamma.
Mm-hmm.
What's the size of this matrix? I'm going from 3 by 1 to 4 by 1. So this better be a what? A
1 by.
did I say
3 by 1.
is that right? Yeah. So it better be 4 by 3, right?
Mm-hmm.
I better have a 4 by 3. So if you tilt your head and split, you can see that the matrix should be what? So this times that should give me these. That tells me I should have a 1, 1, 1. This times whatever's here should give me b plus 2c. So that gives me 0, 1, 2, 0, 1, 2, and then yet again 1, 1, 1. And there you go. That's the matrix of this linear transformation with respect to these basis choices.
I thought you did this in this example. You are going to give them to find the T inverse beta gamma.
T inverse, oh,
Yeah.
that would be harder. Impossible.
Impossible?
I think so.
Hmm.
Well, inverse, what does that mean? Well,
That means you are given.
well. I guess if you think of the inverse from the range here, you could do it.
Mm-hmm.
Well, I mean, I guess that's the accepted thing, right? Oh, anyway, that was not what I was doing today. So let me erase this and give us yet another example. We try to come up with a weirder linear. I mean, there's lots of linear transformations that are out there. I suppose I could do a homework problem for them. You'd like that, wouldn't you, Bailu?
Mm-hmm.
What, Bailu has agreed to me doing their homework? Oh my goodness.
Oh, no. I mean, example is fine, but not the homework.
But the homework would be more helpful,
Yeah.
wouldn't it? I mean, really.
I found what you said about Missouri. Why you pick Missouri?
Don't run tape.
Oh.
We're mission 5, right?
Yeah, I think so.
All right, are we still taping?
Mm-hmm.
We're still taping, aren't we?
Mhm.
Okay, great. Okay, this one will be kind of like 87. but not the same exactly. So let t of A equal to BAB. All right. For B equal to, let's say, 1, 2, 3, 4. All right. So I want to find the matrix of this linear transformation. And I'm going to use the standard, sort of the usual basis for 2 by 2 matrix, using the one we just used for gamma in the previous example. First of all, is this a linear transformation? I wanted to talk about that briefly. It's easy to show it is, actually, because if you have t of A1 plus A2, right, then you've got B A1 plus A2 B, which is BA1B plus BA2B, and you can easily put a constant here and put it here and put it here, and so that will imply that T is linear. So that we don't, I mean, you might worry it's nonlinear because there's like a B and a B, but the B and the B don't appear as the argument of the transformation. They're just part of the formula. It's okay. All right, so the question then is, what would the matrix of this be if I look at T going from, say, R2 by 2, of course, to R2 by 2 with respect to basis, let's say, gamma, because I used it last time, I'll stick with it, E11, E12, E21, E22, the usual thing. So yet again, I have to look at T of, well, A, B, C, D. It's a natural thing to look at. What happens then? Oh, this is kind of a pain, but, you know, we'll survive. We actually have to multiply this out, right? Fortunately, Bayla was here, so she'll make sure I don't make any sort of hideous mistake at this point.
I was going to suggest you to change 1, 2, 3, 4 to 1, 2, 3, 1.
Too late. All right, so this gives me what?
A plus 3B, and C plus 3D, and 2A plus 4B, and 2C plus 4D.
All right, one more. Why did I do this? All right, A plus
So
3B.
A plus 3B plus 2 times
So 2C
2C
plus
plus
6D.
So
3A plus 9B.
plus 4C plus 12D.
Okay, and
this is A 2A plus 4B plus 4C plus 8D. 2
oh, 4, okay.
4C plus 8D.
Yeah.
And this is 6A plus 12B plus 8C plus 14D.
What?
16.
Okay. I'm not going to draw the picture this time. I hope you guys can forgive me. You're like, hey, I thought you said you draw the picture. Okay, I admit it. I don't always draw the picture. Fine, you got me. So T of A, B, C, D. Okay, in the gamma basis would be what? It's, so you got A plus 3B plus 2C plus 6D. The second thing would be 2A
Plus
4B
plus 4C plus 8D.
8D. Then
3A plus 9B plus 4C plus 12D. And 6A plus 12B plus 8C plus 16D.
cool, they were already in order.
Yay.
Of course, that's equal to the matrix we're looking for, multiplied by the coordinate vector of this, which is A, B, C, D. So, I mean, I'm saying if this is V, then the coordinate of V with respect to gamma is A, B, C, D. Okay, so, all right. So this again is T of V in the gamma coordinate. This is V in the gamma coordinate. That would make this thing we're about to write down the matrix with respect to the gamma basis. When we use the same basis for the codomain and the domain, then we just say the matrix with respect to the basis gamma. And some people would just write T sub gamma. I write T sub gamma gamma just to be pedantic, but you know, you see that that's not entirely needed. You might argue none of this is needed. I kill you. All right. 1, 3, 2, 6, 2, 4, 4, 8, 3, 9, 4, 12, 6, 12, 8, and 16.
I have a question.
You have a question?
Yeah. What if we do the row reduce for the T gamma gamma?
What if we do row reduction on T gamma gamma? I don't know. I imagine interesting things might happen. I mean, my intuition here is that, I mean, the rank of this linear transformation is at most 2, because it's built with something that's rank 2, so you can't get something for nothing. And so to me, like intuitively, I don't expect there to be more than rank 2, because it's just built with this matrix which has rank 2. So there's probably like a lot of redundant, I mean, there's going to be a 2-dimensional, there's going to be lots and lots of 2x2 matrices which this thing sends to 0, corresponding to the fact that this row reduction, I think that when you do the row reduction on this, you're just going to have 2 non-zero rows. But you are trying to trick me into talking about the thing we're going to talk about Monday, which is the topic of why rank is rank, and why is nullity is nullity. So, but I'm going to say that for Monday, start class. So I think that suffices, folks. I won't make you listen to me. I mean, you don't have to listen to me at all if you don't want to by now. You should realize that. But it would probably be helpful if you did. There are other examples in the notes you can look at. If you guys have questions, just email me. Thanks.
Okay.